Okay, so let's picture this. You have a truly revolutionary idea for a new product. Maybe it's a cutting-edge serum, something built around a trending active ingredient, let's say a highly unstable form of vitamin C.
Right, a tricky one.
So you build the formula in the lab, it looks gorgeous, feels silky smooth, you're feeling great. You send it off for stability testing.
Then you wait.
And 2 weeks later, disaster. It is curdled, or maybe it's turned this suspicious shade of brown. Or worst of all, it's just completely separated.
And that's the moment, right? That separation or color change, it immediately kicks off what our sources call reactive troubleshooting.
Panic mode.
Total panic mode. The clock is ticking, and the first instinct is just swap out an oil, add a little more thickener, maybe try to fix the color with, one more thing.
Right.
But here's the powerful insight we found again and again in the research from professional cosmetic chemists. Nearly all of those catastrophic late-stage challenges, they were shaped much, much earlier.
So the consensus among the experts is pretty brutal, but true. You're trying to fix a faulty building with a new coat of paint.
Exactly.
The issue isn't usually that one single oil or that single active. The true problem is, in the original system architecture, the functional ingredients.
Which were either designed incorrectly or, and this is more likely, completely ignored in favor of the flashy stuff.
That's right. And that's our mission for this deep dive. We're going to give you a framework for understanding product efficacy and stability by looking at the foundation.
We're digging into the hidden logic of formulation. Why these big failures, stability, efficacy, the way it feels to the consumer, are so rarely fixed by reactive tweaks.
But instead by intentionally designing that functional system from the very beginning.
Okay, let's unpack this.
So the first crucial step that formulators often skip, especially when they're really obsessed with the new active, is defining the desired experience.
It sounds like a marketing brief, doesn't it? Not a chemistry problem.
It really does. But our sources stress this has to happen before you even start drafting an ingredient list.
It's the difference between, say, building a house for a specific climate versus just stacking bricks and hoping for the best. You have to ask these really fundamental questions that come before everything else, before the active. Is this product going to be light, like a refreshing gel, or rich, like a dense cream?
And what about the viscosity? That's how thick it is, how it flows.
Exactly. Is it going to be fluid and watery, or will it be more cushiony?
And what about the feeling once it's actually on the skin? We're talking about spreadability, how fast it absorbs, and the dreaded afterfeel.
Yes. Does it leave a soft, matte finish, or more of a protective, dewy film?
All of that matters.
It matters immensely, and this is where the conversation fundamentally shifts. You, the consumer, you might be paying for the long-term benefit of the retinol or the hyaluronic acid.
Sure.
But you experience the product through touch, spread, and appearance in the first 3 seconds of using it.
So if it's greasy or if it pills up, and those tiny flakes start rolling up on your skin, you just stop using it.
You stop using it entirely, often within the first week, which means that expensive, cutting-edge active ingredient never even gets a chance to work.
That's a great point.
We can actually reframe the functional ingredients, the thickeners, the emollients that dictate that feel as the compliance ingredients.
The compliance ingredients, I like that.
They ensure the user actually sticks with the routine long enough for the active to even be relevant. If that sensory framework isn't intentional and delightful from the start, you're stuck trying to fix the feel later.
And that often means you have to compromise the stability to do it.
You got it.
That's a fascinating reframe. The sensory goal is actually the technical framework. It sets the rules for all the ingredients that come after.
So let's get concrete about this architecture. When we say functional ingredients are the backbone, we are talking about the components that create the physical structure of the product.
The scaffolding.
That's the perfect word for it, the scaffolding.
So what are we listing here? What falls into that category?
We're talking about the big structural players. First, emulsifiers, which are the glue holding oil and water together.
Okay.
Then the oil phase itself, solvents and emollients. We have rheology modifiers, think thickeners or gelling agents, which dictate flow.
Right.
Humectants, which manage water. Preservatives for safety. And surfactants, which can influence everything from foaming to how mild it is.
So these components together, they determine structure, stability, how a product flows.
Everything. If you choose an anionic emulsifier, for example, that single decision immediately imposes constraints on every other ingredient you can possibly use.
It defines the universe your active ingredients have to live in.
Perfectly put. They determine how thick the product is, how it melts on the skin, and this is crucial, how resistant it is to stress like heat or cold during shipping and storage.
And if they're just selected randomly, or maybe just based on price.
The whole system is precarious.
Which leads right to this idea that ingredient selection has to be a consequence of the system design, not the starting point.
Yes.
We can't just assume the active ingredient will fit. It has to participate within the system you've already built.
That is the critical point. Let's use the niacinamide example. Everyone loves it, it's highly effective, and it's often used in these high percentages, like 5% or 10%.
But it's known to cause some difficulties in the lab.
It is. It has specific pH preferences. So if you formulate a base system that drifts too high in pH,
It becomes too alkaline.
right, the niacinamide can partially convert into nicotinic acid, which is what causes that temporary, unpleasant skin flushing and irritation.
Oh, that's what that is.
But even if the pH is perfect, you have to think about ionic strength.
Okay, explain ionic strength for us.
Think of it as the total concentration of charged particles like salts or acids just floating around in the water phase.
Got it.
Many of the most common, most effective thickeners used in creams, these popular rheology modifiers, are actually polymers that rely on electrical repulsion to create their structure. They swell up because all the little chains are pushing each other away.
So when you dump a highly ionic ingredient like niacinamide into that polymer network,
You flood the zone with charge. That charge collapses the structure of your polymer, and your beautiful, thick lotion turns into a thin, unstable soup overnight.
and the formula didn't fail because the niacinamide was bad?
No. It failed because the system architecture, that polymer thickener, was just incompatible with the active's required constraints. You fix it by going back and redesigning the backbone, not by blaming the niacinamide. Building on that idea of constraints. What's fascinating here is how the sources talk about this. They urge formulators to see that every single ingredient comes with built-in limitations.
And to see them as predictable behaviors, not as flaws.
That's it. It's a subtle but really important distinction.
So these behaviors define the boundaries a formulator just has to know right from the start. Things like the pH range an ingredient can tolerate, its thermal sensitivity,
How much shear force it can handle.
shear being the mixing force.
Right, the mechanical force. And you have to know precisely how it behaves during manufacturing. Knowing these behaviors gives you a playbook for troubleshooting.
So if your batch suddenly thins out after homogenization, you don't panic.
You don't panic. You check the spec sheet for your emulsifier or your thickener. Did we go over the maximum recommended temperature? Did we apply too much shear for too long?
And speaking of that processing step, the sources argue that it's so critical, it's essentially part of the formula itself.
It absolutely is. The details of the process are the final structural components we're talking about. Which liquid phase gets poured into which? At what precise temperature? For how long do you mix it?
And when do you add the sensitive stuff?
Yes, when do you introduce the ingredients that can't handle heat or mechanical stress? Even changing the order of addition for things that seem simple, things that are perfectly water-soluble, can completely change the environment.
Let's use that specific anecdote from the source material about allantoin. It's a really common skin conditioning powder.
Very common.
It's water-soluble, yet formulators often run into issues with it. Cloudiness, or even visible crystals forming.
This is a perfect, subtle demonstration of how a system can change in real time. Think of the water phase in your formula as a saturated sponge, ready to absorb things.
Okay.
When you start adding high levels of humectants ingredients, like glycerin or propanediol, those are highly efficient at grabbing and holding onto water molecules.
So the water becomes kind of busy. It's already occupied.
Exactly. So then when you try to introduce allantoin later, after the water has already been loaded up with glycerin, the allantoin struggles to find enough free, available water to fully dissolve.
Because its solubility is much lower.
Much lower. So it crashes out of solution, often crystallizing later on during cooling or storage. A new chemist might blame the raw material, but the problem was they violated the capacity of the solvent system they had just created.
That's incredible. The allantoin molecule didn't change, but the environment it was dropped into completely changed its behavior.
And this sensitivity to processing becomes even more important when you're dealing with advanced structures like lamellar emulsions.
Well, lamellar emulsions. That sounds very technical. What are they?
They're structured systems designed to mimic the natural lipid layers of your skin's barrier. They're organized into these delicate, repeated layers, like sheets of wallpaper stacked together.
And that gives them a specific feel.
A very desirable, cushiony, non-tacky sensory experience. But if you apply excessive shear, or you homogenize for too long during manufacturing, you physically tear those layered structures apart.
So you start with a formula that's designed to feel luxurious, but if you mix it too hard,
You destroy the very architecture that provides that desired feel. You end up with just a regular, non-structured emulsion, often with a greasy feel and poor spreadability. The ingredient list was perfect, but the processing, the final architectural step, failed.
we've established you need this strong functional foundation. But not all problems are, polite enough to show up right when you make the batch.
Yeah.
The sources really emphasize that some of the biggest and most expensive surprises only appear much, much later, sometimes after a product is already in production.
And those delayed outcomes are almost always traceable back to an under-supported functional system. Take preservation, for instance.
Right.
A formulator selects a preservative system, feels secure, but the effectiveness of that preservative isn't static.
It depends on the environment it's in.
It does. It depends on something called partitioning. Most preservatives need to be in the water phase to work, but if your formula is very oily or has certain emulsifiers, the preservative molecules can get pulled into the oil phase.
Leaving the water phase where the microbes actually live underprotected.
Exactly. The system architecture has effectively neutralized your preservative, and this only shows up weeks later during microbial challenge testing.
So you chose the right active preservative, but the backbone you built made it inactive.
You got it. Another classic late-stage problem is color change, specifically browning. A fresh batch of serum looks perfectly clear, but 2 months later it's turned pale yellow or even amber.
And we usually assume that's the active ingredient oxidizing, right, like with vitamin C.
Often, yes, but even then it's a system failure. It means the functional system didn't adequately support the active with enough antioxidants or chelating agents.
Or even just the right packaging.
Or the right packaging to prevent oxygen exposure. But sometimes it's simpler. A common fragrance component, like vanillin, is known to interact with other things in the base, causing a brown tint over time, especially in high pH systems.
So you could spend weeks blaming the vitamin C when it was actually your fragrance oil reacting with the buffer.
It happens all the time.
And finally, the ultimate performance surprise, sunscreens. You can load a formula with high percentages of UV filters, but the SPF number that comes back from testing is low. How does that happen?
Because SPF is a test of uniformity, not just quantity. We come right back to the functional backbone. The job of the UV filter is to create a seamless, continuous protective film over the skin.
And if the thickeners and gelling agents in the formula don't create a stable, spreadable base,
The UV filters clump up.
you end up with patches of high protection and big unprotected gaps.
Precisely. A superior SPF rating often comes from choosing the right film-forming polymers and functional oils that ensure perfect distribution. It's much more about that than just cranking up the percentage of zinc oxide.
The structure of the system is doing the real work.
If we connect this to the bigger picture, the source material's core message is really about synthesis. Formulation is intentional system design. It's not about memorizing quick fixes.
Failures are almost never about one single evil ingredient.
No, they reflect how the entire functional system was designed, understood, and processed as a whole.
So what does this all mean for you, the learner, whether you're just analyzing ingredient lists or actually managing product development? You now have this critical framework for assessing product quality. Stop looking only at the flashy active ingredients and start looking at the foundation. Is this formula water and oil or oil and water? What kind of rheology modifiers are supporting this structure?
Because that functional backbone dictates everything.
It dictates the consumer experience, it dictates stability, and it dictates the active's ability to even perform.
And if you want to take this knowledge and immediately apply it in your own critical thinking, consider this final provocative thought based on those late-stage preservation issues we discussed.
Okay.
Given that preserving a product is so hard because the system itself often works against the preservative, you might consider researching which common functional ingredients, say specific humectants or common non-ionic emulsifiers, are known to antagonize or deactivate typical preservative systems.
So you can avoid them from the start.
Or at least account for them. If you start by designing a backbone that supports preservation rather than fights it, your actives stand a far better chance of making it to market safely. It all connects back to the foundation.